Survey design. Many problems that arise in applications can in fact be solved efficiently by reduction to maximum flow, but it is often difficult to discover when such a reduction is possible. In the next few sections, we give several paradigmatic examples of such problems. The goal is to indicate what such reductions tend to look like and to illustrate some of the most common uses of flows and cuts in the design of efficient combinatorial algorithms. One point that will emerge is the following. Sometimes the solution one wants involves the computation of a maximum flow, and sometimes it involves the computation of a minimum cut. Both flows and cuts are very useful algorithmic tools. We begin with a basic application that we call survey design, a simple version of a task faced by many companies wanting to measure customer satisfaction. More generally, the problem illustrates how the construction used to solve the bipartite matching problem arises naturally in any setting, where we want to carefully balance decisions across a set of options. In this case, designing questionnaires by balancing relevant questions across a population of consumers. The problem. A major issue in the burgeoning field of data mining is the study of consumer preference patterns. Consider a company that sells K product and has a database containing the purchase histories of a large number of customers. Those of you with Shoppers Club cards may be able to guess how this data gets collected. The company wishes to conduct a survey sending customized questionnaires to a particular group of N of its customers to try determining which product people like overall. Here are the guidelines for designing the survey. Each customer will receive questions about a certain subset of the products. A customer can only be asked about product that he or she has purchased. To make each questionnaire informative but not too long so as to discourage participation, each customer I should be asked about a number of products between CI and CI prime. Finally, to collect sufficient data about each product, there must be between PJ and PJ prime distinct customers asked about each product J. More formally, the input to the survey design problem consists of a bipartite graph G whose nodes are the customers and the products, and there is an age between customer I and product J if he or she has ever purchased the product J. Further, for each customer I equals to 1 to 3 until n, we have limits Ci which is less than or equals to Ci prime on the number of product he or she can be asked about. For each product j equals to 1 to 3 until k, we have limits pj less than or equals to pj prime on the number of distinct customers that have to be asked about it. The problem is to decide if there is a way to design a questionnaire for each customer so as to satisfy all these conditions. Designing the algorithm. We will solve this problem by reducing it to a circulation problem on a flow network G' with the demands and the lower bounds as shown in figure 7.16. To obtain the graph G' from G, we orient the addresses of G from customers to products and nodes S and T with addresses Si for each customer I equals to 1 to 3 until n, addresses JT for each product J equals to 1 to 3 until K, and an age TS. The circulation in this network will correspond to the way in which questions are asked, the flow on the age. Si is the number of products included on the questionnaire for customer I, so this age will have a capacity of Ci prime and a lower bound of Ci. The flow on the age JT will correspond to the number of customers who were asked about product J, so this age will have a capacity of Pj prime and a lower bound of Pj. Each age ij going from a customer to a product he or she bought has capacity 1 and 0 as the lower bound. The flow carried by the age Ts corresponds to the overall number of questions asked. We can give this age a capacity of the summations of Ci prime, summing for all I, and a lower bound of summations of Ci, summing for all I. All nodes have demand 0. Our algorithm is simply to construct this network G' and to check whether it has a feasible circulation. We now formulate a claim that established the correctness of this algorithm. Analyzing the algorithm. The graph G' just constructed has a feasible circulation, if and only if there is a feasible way to design the survey. Proof. The construction above immediately suggests a way to turn a survey design into the corresponding flow. The age ij will carry one unit of flow if customer I is asked about product J in the survey and will carry no flow otherwise. The flow on the axis Si is the number of questions asked from customer I, and the flow on the HJT is the number of customers who were asked about product J. And finally, the flow on HITS is the overall number of questions asked. This flow satisfies the zero demand, that is, there is flow conservation at every node. If the survey satisfies these rules, then the corresponding flow satisfies the capacities and the lower bounds. Conversely, if the circulation problem is feasible, then by 7.52 there is a feasible circulation that is integer valued, and such an integer valued circulation naturally corresponds to a feasible survey design. Customer I will be surveyed about product J if and only if the age ij carries a unit of flow.